All right. We ended the previous lecture by writing down the equation of motion that we obtained from the Lagrange equations. And as we look upon this, we can make several observations. For one thing, this equation has exactly the same form as for a one-dimensional harmonic oscillator. So we have, if you will, the mass term here, the second derivative of the position coordinate, plus this Vij, which here appears to play the role of the spring constant, multiplied with this perturbation, eta. So that's one thing. What this equation does is that it provides us with a solution for eta I as a function of time, which in turn describes how the system moves or behaves near equilibrium. Now I said that there's a strong resemblance here between this equation and the 1D harmonic oscillator, but at the same time there's a crucial difference. And that is that we have a sum here. We have a summation over J, both for the kinetic and potential energy. So in fact, this is a set of coupled second-order differential equations. So you can imagine that we have a set of harmonic oscillators or springs that we have attached to one another. In this general case, we will get something like this. Now, in order to proceed, at least analytically, we have to make some sort of assumption about what the solution looks like. How do we expect the system should behave? In other words, we have to make some assumption about the form of eta, the mathematical form. So if this equation describes a set of coupled harmonic oscillators, if we can think of it in that way, how would you propose that we can write eta? Or like qualitatively, how would you expect eta to behave? Mm-hmm. So basically it should correspond to some harmonic oscillation. Yeah. We have no damping terms here. So in principle we should be able to get a sustainable harmonic oscillation, as you say. So something like this, where A is a complex, so that we get the most general solution, both the cosines and the sines. And I've used index I here, but I hope you're able to differentiate it from this imaginary unit in the exponent. And let me just underline that the real motion is provided by the real part of eta. We're just using an imaginary representation to make the calculus a bit simpler. Instead of dragging along all these cosines and sines and combining them with trigonometric rules and getting a headache, we're just writing them in a compact notation like this. But the real motion is then provided by this. And from this expression, we see then that we get precisely this combination of cosines and sines that you said.
Excuse me?
Yep.
From the expression we have in the box on the board, can we conclude that the etas do not interact with one another? Because as I read it, that's what you're saying with the expression.
Yeah, definitely. That's a very good question. So we're saying here that we can write the perturbation for the amplitude of the perturbation related to generalized coordinate qi in the following way. And apparently, it seems to be completely independent of what happens in the other directions. But as we shall see, this is not exactly the case for the following reason. We have two additional components here. We have the amplitude and we have the frequency. Now, would you agree that all the information about the interaction between the various directions of perturbation are contained in these matrices? In particular, it's Vij. And as we will see in just a little while, these so-called eigenfrequencies are obtained precisely from this matrix. So by writing it in this way, we still have information about the interactions in the system contained both in the amplitude and eigenfrequency.
But for example, in the case of a coupled oscillator, wouldn't we expect the amplitudes to change with time as well?
I see what you mean. Just a sec.
Wouldn't that describe a loss of energy?
Yeah, possibly. I guess it would depend on how exactly they would depend on time. So in principle, if one of the amplitudes were just growing or diminishing, then we would have either an injection or loss of energy, which would be inconsistent with the conservation of energy.
I think the amplitude of one the oscillators would be dependent on a cosine term. The other amplitude would be dependent on a sine term, such that the total energy is conserved.
I see what you mean.
Yeah. But I think you need an external potential.
That could be. But in a sense, I mean, the varying amplitudes we get already from this expression here, right? You can think of it as an amplitude varying as a combination of cosines and sines. So this describes essentially how the amplitudes evolve with time, right? Because the real and imaginary parts of AI can be different. So I think that the case that you described should be covered by these ansatz, in fact. All right, so if we're comfortable with this ansatz, we can try to see if it actually solves the system and what kinds of solutions that we find. So if this is indeed a solution for our equation of motion, well then this equation should be satisfied. And it places a condition on Aj and also on the frequency omega. This is a type of equation system that is probably quite familiar to you. It's a set of homogeneous equations. Now, if we interpret V and T as the matrices, since we have these elements of Vij, and we interpret A as a vector, we can write the equation like this. So A is now a vector containing all the entries of A, A1, A2, etc. And V and T are just kinetic and potential energy matrices. Okay, so if this is the equation we have to work with, can we say something right away about which conditions that need to be present in order for this to be a solution? Well, I see one obvious solution for A, which I guess you also see, yeah?
If A0 is non-zero,
Mm-hmm.
and we want non-trivial solutions, we need the determinant of the coefficients to be non-zero.
So the obvious solution is A equals 0. That is the solution. But as you say, if you want a non-trivial solution, non-zero solution for A, then we require this matrix to have a determinant which is equal to 0. So that's the condition that needs to be fulfilled in order to have a non-trivial solution if our solution looks like this. So let's try to write out this determinant condition. the reason for why I'm writing it in this way is to make you see that this is in fact an nth degree equation for omega. So basically you can think of this as a kind of an eigenvalue problem for omega. You get an nth degree polynomial which has to be solved in order to find omega squared here. So in general, when we solve this equation, we're going to find n different solutions for omega squared. So we characterize each of these different solutions with an index alpha. Now, depending on what this matrix is, we may in some cases find that we have some degenerate solutions, that not all of these are distinct. And we'll consider some of the implications of this later. So keep in mind that omega alpha are known as the eigenfrequencies of the system. Now, if you just revert to the question that you posed, you see here that when determining omega, we have all these information about the interactions in the system. So in this way, the solution will actually depend on how the system interacts. Now, I would suggest to you that omega squared has to be positive and real. How can I state that as a fact?
Well, the imaginary omega would correspond to exponentially increasing or decreasing function.
Yeah. This would be inconsistent with the conservation of energy that we have. All right, so as long as we know, as long as these matrices T and V are known, we can determine all the eigenfrequencies simply by solving the system. So we assume now that these eigenfrequencies are known. So if you know what all the eigenfrequencies are, well, we have at least partially solved the system, because we now know how the time variation of these amplitudes of the perturbations behave. But there's one more part that we have to determine, and that is the actual amplitude of the perturbation. So keep in mind the solution looks like a exponentially of minus I omega t. So we know omega, but we still have to determine the amplitude. So in other words, we're basically looking for an answer to the question, what parts of the system are moving and by how much are they moving when we're considering an oscillation mode alpha. So in general, we have n, small n number of solutions for the eigenfrequency. These are all possible solutions of the system. So if you consider one of them, that's one allowed oscillation mode of the system. So the question is then, what is the corresponding amplitude? And I'm now attaching an index alpha to the amplitude to highlight the fact that we're considering a specific eigenfrequency. So eventually we're going to have a lot of indices in the problem. So let me just clearly state what the physical meaning of these indices are. AI alpha corresponds to the amplitude of the perturbation along the generalized coordinate direction QI when the system is in the mode alpha, corresponding to the eigenfrequency omega alpha. So that is the meaning of these indices. So to determine these amplitudes, we have to consider again the same equation. So I've now attached alpha here just to indicate that we're considering a specific eigenmode. And this notation might be a bit confusing because in this case, there's no sum over alpha. We have a sum convention for J, but there's no sum convention for alpha. So let me just write that to make it absolutely clear. So these are n equations, and they can be used to obtain n minus 1 of the elements in this amplitude vector that we introduced. That might seem a bit strange. We have n equations, but we can only determine n minus 1 of the elements. Does this make sense? And if so, what is the reason for it? Any ideas?
We should be able to scale the system without changing the equations inversely, so all the amplitudes will be parameterized by C1.
Yeah, you're right. If I understand it correctly, you're saying that you can always scale the system, meaning that you could multiply the amplitudes with a constant factor. So you see now that if AJ alpha is a solution for the system, well then any constant multiplied with this is also a solution, because I just multiply with constant on both sides and still get 0. So fortunately or unfortunately, depending on what you're looking for, you can only determine n minus 1 of these elements, because one of these elements, for instance the first one, if we just choose the first one by convention, will always be undetermined up to a multiplicative factor. So even if you have n equations, we only can determine n minus 1 of these elements, which will be expressed in terms of the last one. Do you see how I mean? Yeah. So we see that since A is in general a complex quantity, meaning that it has a real part and an imaginary part, and both need to be determined, we need 2n initial conditions. And this is consistent with the fact that we need 2n initial conditions to fully solve the Lagrange equations. All right, so the eigenfrequencies are obtained from the matrix on the far left side, which we know, since this is assumed to be known. We know the kinetic energy matrix and the potential energy matrix. And we now also have a prescription for how to obtain the amplitudes in the problem. I mentioned that this matrix may or may not have all distinct solutions to the eigenfrequencies. There may be a situation where the matrix is such that some of the eigenfrequencies are degenerate. But we'll now consider a special case which is of particular importance, and that is the case where all of the eigenfrequencies are in fact distinct. So what we'll do now is to try to analyze the system further under this assumption. And when you're faced with a problem, you can easily check just right away if this condition is indeed satisfied. You basically just calculate the determinant of this matrix and check if the solutions are distinct. If it's not, if some of the solutions are degenerate, then this method has to be modified. So keep that in mind. What we're about to do is, strictly speaking, only valid for degenerate eigenfrequencies. Did I say degenerate? For distinct eigenfrequencies. what we'll show is that in the special case where all the eigenfrequencies are distinct, these amplitude elements are in fact proportional to the minor delta I alpha. And by minor, you may also be familiar with this as cofactor from linear algebra. This minor or cofactor is delta I alpha is obtained from this determinant by removing the ith row and the column number alpha. So if you do that and then calculate the determinant, you get the minor delta I alpha. So that then gives us a way of determining the amplitude elements, again, by calculating a subdeterminant of this matrix. So this matrix is truly the key to solving this type of problem. And let me also mention that we have to be careful to include the appropriate sign for the cofactor. It's given by -1 to the power of I plus alpha. So for instance, delta 1,1, just to be clear, delta 1,1 is obtained by removing this column and this row, and then calculating the determinant of what's left, and multiplying with the appropriate sign, which is a 1 in this case, +1. You can prove this in general for an arbitrary matrix, but what we'll do is just to give you an example for the specific case of a 3x3 matrix, just to show you the sort of principle for how to derive it. And hopefully you can then accept this, or if you will, extend it to a more general proof. That thing here is supposed to be a proportionality constant. So we consider the case where n equals 3. And consider to begin with the equation for alpha equals 1 and I equals 1. So let me first write down the general form of the equation. I've now written out the sum explicitly over j. So this alpha is fixed. It's not a summation over alpha. So let's now consider the case where alpha and I are both equal to 1. This is the general equation of motion, so we get forget that. Where I've just written out the sum. So this is essentially an equation for these amplitude coefficients. Sorry, it should be 1 here. Okay, so we've stated now that for the case where all of these eigenfrequencies in the system, omega 1, omega 2, omega 3, are distinct, we should have proportionality between the amplitude elements and the cofactors. And I may write this general determinant in the following way. So what I've done here is I've expanded the determinant in terms of the minors or cofactors delta II, delta 1, 1, delta 2, 1, and delta 3, 1. So this is essentially the first element in the matrix, the top left element, multiplied with the rest of the determinant. And then I take the second element along the first row and multiply with the corresponding cofactor. So I've just expanded the determinant along the first row. Now, V and T are symmetrical, as we saw. Okay. So let's now check if we indeed have that these elements are proportional to the cofactors, are these two equations then consistent? So I'm writing the constant of proportionality as C alpha. I'm now inserting this here at the same time as I'm exploiting this symmetry of the V and T matrices. So I'm interchanging the indices here and here. So compare now these two equations. We see that they're consistent as long as C is non-zero. So this completes the proof, or proof, for 3 dimensions. Okay, so a lot of indices, and we'll continue with this in the next lecture, but let me just outline again that I here corresponds to the movement along the generalized coordinate qi, and alpha is the eigenfrequency alpha of the system. Okay, thanks.